Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at ventilators. In this video, we will look at some of the control schemes for ventilators. What are the control systems that is required for ventilators? Modern ventilator closed loop control system, one that is provided by a company called Drager, called Oxygen. It's a name of a product, and some of the control schemes that are there, advanced control and target control schemes. So, ventilators depending on the requirement can have different control schemes. The selection of control schemes essentially depends on the use case of the specific use of ventilator for the particular disorder. In some condition, volume control is more important. For example, in the case of ARDS, what is ARDS? Acute respiratory distress syndrome. This is acute respiratory distress syndrome, where in these cases, if more volume of oxygen is delivered, then it can cause volutroma. Volutroma is a form of ventilator induced lung issue, is it not? Lung pathology is a form of ventilator induced problem. For these cases, volume will have to act as a control variable. The volume control schemes will make sure that that you set a volume that is safe for that. Now, what is such a thing? What is a safe volume? There is such a thing called as a safe volume. Note, in ARDS, the lung compliance is reduced or compromised greatly. So, that means that the compliance cannot be a factor in your governing equation. So, because lung compliance is already greatly compromised. Now, because of excess volume of oxygen that is pumped in, what happens is that there is a distension that happens at the alveolar end, which can cause mechanical wear and tear at the alveolar, at the cellular level. It can cause mechanical damage, which is a dangerous situation, okay, because that is not, that is essentially an irreversible operation, right. So, this injury is irreversible and can cause a serious problem, right. So, note that different alveoli have different opening and closing pressures. So, there is a need to have a heterogeneous control scheme. So, there is no specific flow control scheme, because flow itself is the first derivative of volume. We already discussed this. So, flow can be manipulated with a given volume itself. Sometimes pressure plays a major role in the case of restrictive disease, depending on the situation. What this says is that depending on the particular condition, you need to choose the control scheme. In the case of restrictive diseases, pressure delivery and amount of pressure delivered is to be controlled. Okay. So, pressure control schemes will allow the clinician or the physician to set particular parameters of pressure, like maximum pressure, because that is because above the maximum pressure it can cause again damage to the lungs, inspiratory pressure, etc. In volume control schemes, although the volume is a control variable, there is a limit. Pressure limit is adjusted for safety purposes. I already discussed this in one of the previous videos. In pressure control schemes, the maximum delivered volumes are also controlled to make sure that volutroma type of situation does not happen. So, these are all the various things that are simultaneously controlled. Here is a block diagram, a typical block diagram based on the inputs that we gave. AI generated this block diagram, a typical block diagram for a ventilator. There is a controller Actually here we have said P of t equal to k, or V dot of t is k, but actually it is not a P controller, but rather a PID controller. It will be a proportional integral derivative controller and a hardware effector, and the patient, this output is given to the patient, and there is a inspired flow, and this inspired flow is integrated over time. Note that V dot is flow. So, if you integrate this over time, you get the volume as the input to this controller, and pressure that is actually measured at the patient end, that is also given as an input to the controller. That is so this is the set volume or the set pressure. These are the measured, these are the measurements. These are the measured volume and the measured pressure. Then the controller acts on this. What is the gain of this system? What is the, this is a of course this is a feedback system. What is the gain of this system? The gain of this system is H of s is G of s divided by 1 plus G of s, right, 1 plus G of s H of s. Is it not? This is the point is there is a open loop gain or forward gain, and then there is a feedback gain. Okay, something to keep in mind. Now compare this to your AC HVAC system or a thermostat. You have a set point, the AC keeps cooling until the set point is reached, after which it will stop cooling, something like that. What you need is a smoothly operating system, for example comparable to a cruise control. Well, in a cruise control, in a car, in a cruise control system, you can either control the engine power or speed. These are comparable to volume and pressure, right. But on flat terrain, these two are essentially the same. If you control the power, then you are controlling the speed. But depending on whether the terrain is hilly or uphill or downhill, the pressure and the power and the speed difference, speed relationship, likewise the volume and the pressure relationship in the lung may change depending on whether the patient is having what type of disease. Depending on that, it will change. So power is not equal to speed in uphill or downhill slopes as in cruise control, for example. Right. Here is an advanced patient dependent control system that is provided. There are some protective guidelines, some values of pressure and volume that is given, and some protective ventilation is provided, and a carbon dioxide target value and an oxygen target value is provided. So there is a specific carbon dioxide controller, and there is a specific oxygen controller that is there, and then there is a demand controller, and this is given as input to the actuator system of the ventilator and then to the patient. And then you measure the outputs from the patient. What are these? This is the airway pressure, is it not? PAW means PAW means airway pressure. Okay. This actually includes both the elastic and the resistive components, is it not? There are two components, we already saw this. The pressure is a function of elastance and resistance. Right. Then the tidal volume, VT means tidal volume. Okay. Right. You will have to correct this for compression volume, and depending on the specific condition you may have to correct this. Then EtCO2, what is EtCO2? End tidal carbon dioxide, is it not? This requires a technique called capnography. You need a capnography. Check what this is for your own understanding. Check what is end tidal carbon dioxide and how is it measured using capnography. If you want to provide this as a feedback to your controller, then you need to measure this end tidal CO2 using capnography. Okay. And note that it is also affected by the volume and flow mismatch between volume and flow. Then you have PaCO2, like you have PaO2, you have PaCO2. This is actually the gold standard. This is what you would ideally like to measure for as a feedback, as a parameter to your feedback system, but it requires arterial gas analysis, blood gas analysis you need to do, which is not actually a simple process and may not be real time. So, may be time consuming, may requires analysis of arterial blood gas levels. It is not a trivial process. Then of course, you have SpO2. SpO2, PaO2 essentially the oxygen hemoglobin content, this oxygen hemoglobin, this dissociation curve, and you will have to consider the oxygen, consider the oxygen hemoglobin curve and their consideration, and you want to maintain SpO2 at set levels, for example above 96% in relatively healthy patients, and if the patient is having some COPD type of thing about 94, 92%, whatever, some set level, something like that. So, it is like you are interested in managing many different things, like you are, let us say you are driving a car, you are interested in having good fuel efficiency, having good power, at the same time having good control, different parameters. You want to maximize engine life and at the same time you want to maximize fuel efficiency, at the same time have good power and speed. You are optimizing for multiple things simultaneously. Likewise, in this case also. Yes. One system that is used by Drager is this system called Oxygeny. It is a closed loop oxygen control system that automatically adjusts for oxygen, fraction of inspired oxygen, is it not, to maintain SpO2 within a target range. So, you measure SpO2 and you automatically adjust FiO2. So, it is used quite often in neonatal and pediatric use, and sometimes also used in adults during mechanical ventilation or CPAP. Check what is CPAP, continuous dash 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 dash, check, or high flow oxygen therapy in some cases. This technique uses real time SpO2 feedback and has an algorithm that will optimize oxygen delivery and minimize the amount of manual interventions. This will prevent both hypoxia and hyperoxia. Note that these two things can cause acidosis and alkalosis respectively, improving essentially the patient outcomes. It integrates very well with Drager ventilators and allowing seamless automated oxygen control. So, essentially it is a closed loop control system that measures SpO2 and provides an appropriate amount of oxygen. It is an example of a closed loop control system. Note that this is a commercial model I am discussing, but this is an example of a really good closed loop control system. This is essentially what you want for your system. You want something like this for all the systems. What are the various control schemes? One is set point control. In this case, the operator sets the values that are needed. What are all the various variables I want? Volume so much, time so much, pressure so much, maximum pressure this much, and all selected. And then the control system of the ventilator makes sure that these rules are followed. Right? What are the advantages? The advantage is that it is really simple and relatively its functioning is relatively easy to predict. What are the disadvantages? The disadvantage is that depending on the patient condition, because the operator sets the level at a particular condition, and then the patient may improve or worsen and may need intervention, may need someone to look at that. So, operation of ventilators will not change depending on the patient's need, but will continue to function as per the preset values, as per the set values that are set by the operator. But the patient condition may worsen or may improve, whatever, depending on that. But the set point will not change depending on that. So, this means that the operator will have to periodically keep coming and checking, is this okay? Is this okay every half an hour once, 1 hour once, whatever, depending on the patient condition. So, that is one thing to keep in mind. Then dual control scheme. In this case, ventilator switches between pressure control mode and volume control mode. This allows patients to be accommodated, patient condition is accommodated to some extent and provides some preset value of pressure or some tidal volume. The advantage is that it slightly adjusts, it is able to at least somewhat adjust as per the patient's condition and switch between the two modes, providing an efficient operation. What is the disadvantage? Well, it might be somewhat complicated to control and adjust correctly all the parameters and may need continuous adjustments. This is another one. The third is servo scheme. In this case, the output of the ventilator follows the input, automatically follows the varying inputs. It is a form of negative feedback in which the output and the set point error act as the driving input. So, there is a set point error and the output, both of these serve as the input to the system. The advantage is that the support that is provided to the patient is dependent on the patient's effort on this. The disadvantage is that you need to have an algorithm that will estimate the mechanical properties of the airway, because the airway and its mechanical properties, you have no clue. You are not having any sensors there, you are having sensors only outside. So, you need to find a way to measure the mechanical properties or estimate the mechanical, not measure, actually estimate the mechanical properties. What are these? There are only two, right? Resistance and elastance, compliance, right? So, these you actually do not know, but you need to estimate somehow, and that estimation must be relatively accurate, and that must go as an input to your servo control mode. Then an adaptive control mode. In this case, the target is set in between breaths depending on the patient's condition. The advantage is that it will be able to maintain a given stable set tidal volume even when the mechanics of the lung changes with the patient condition. The major challenge or disadvantage is that sometimes the automatic adjustment that is provided by the controller may not be very appropriate if the algorithm, so all this comes down to the algorithm that is controlling. The assumptions of the algorithm are violated, or there is some mistake, then the physiology or pathophysiology are not matched by the algorithm for this. Then what will happen? The input that is given to the controller may be not very appropriate. Then you have biovariable. In this case, the ventilator automatically adjusts the inspiratory pressure or tidal volume relatively randomly. It essentially simulates the variability that is already observed during healthy breathing, which may improve oxygenation and mechanics of this. The problem is you still need to, you may not be able to achieve the goals, because normal breathing is normal breathing. This is anyway compromised breathing. So, you still need to have a way to make sure that the patient receives the appropriate amount of oxygen and at an appropriate pressure. So, there are disadvantages. Then you have an optimal control scheme. In this case, the system automatically adjusts the targets of ventilatory pattern either to minimize or maximize some overall performance characteristic. For example, work done by breathing. This you need to minimize. And the good thing is that it can adjust depending on the patient situation, patient condition, lung mechanics or inspiratory effort. The disadvantage is that it may not be very appropriate if the algorithm assumptions are wrong, like they said in the previous case. Right. Then you have some intelligent system. This is a situation in which you use AI, artificial intelligence, and some rule based expert system or some fuzzy logic or something like that, some ANN something that can adjust to changing lung mechanics as the patient is improving or as the patient is worsening. The control algorithm itself changes. That our patient is, say the patient is improving, showing some inspiratory effort. According to that, the control algorithm will now be different from what it was, say, 1 hour ago or 1 day ago, for example. Once again, the challenge is that if you have an assumption that is violated, then you have a serious problem. Right. So, with this we come to the end of this video on control schemes. So, in this video we looked at control schemes and modern ventilator control schemes and one closed loop control scheme. So, some things to keep in mind, some things to this complex is not always better. Sometimes simplicity wins. Okay, something to keep. Just because a control system is AI and very complicated, adaptive fuzzy logic control system, doesn't mean that it's a better system. Sometimes simplicity beats complex systems, hands down. That is one. Two is there are computational costs involved. For example, in estimation algorithms, there is a stringent requirement for real-time input. If you have to estimate some parameters, then real-time requirement is there. So, you need to have high-end computing system to be able to compute or estimate some of the things that you are estimating in your control algorithm, something to keep in mind. What if sensors fail? Do you have redundancy, for example? What if sensors fail? Something to keep in mind. Suppose sensors fail, what will happen? That is the other question. And then suppose you are using some model for your airway resistance, compliance, etc., your lung parameters. Note that all models are imperfect. There are going to be some imperfections in your models that will affect your system performance. Do not assume that models, just because you have a model that is generally working, that is generally when you test it is working, does not mean that it will work well in future. Keep that in mind, because what you are testing is for some specific condition, the patient condition might be different. So, then your model will fail or model may not be perfect. So, it is useful to remember that all models are imperfect. If it is a model, that means that it is not perfect. Okay, something to keep in mind. Then neglecting human factors, always or rather consider human factors. If you are having a very complex dashboard and is having too many knobs and too many controls, system complexity might be okay, but there might be, the patient may not be able to control, the operator may not be able to control, then what are you even doing? So, these are some things to keep in mind. Remember, what is our goal? Our goal is to have, in the case of automatic or mandatory control, you want to have, it is like a car that is driving itself, like the self-driving cars of today, autonomous cars of today. They drive by itself, the passenger is not doing it, they are just sitting and then the car is driving. But I am talking about the case where the patient is, where the patient is providing some effort, like in the case of a power steering. I am attempting to turn and then the turn happens further. It is taking cue from the patient efforts, from the driver's effort to turn, is it not? That is power steering or cruise control, for example. Yes, you are looking at an advanced control. These control systems are relatively well developed. For example, these automotive control systems are relatively well developed. You want something like that for your ventilators. You want that type of control, that type of smoothness in your control for your ventilators. With this, we come to the end of this video. Thank you very much for your attention.